Rover 213, a car embodying state-of-the-art refinements in motor manufacturing, refinements in style, refinements in engineering, refinements in quality. Standards of high-quality motor engineering that provide quick, responsive road handling for the sporty, discerning driver, whilst providing high standards of luxury, comfort and prestige to those who have come to expect executive-style motoring from a car which bears the name Rover. Projecting the distinction, efficiency and immaculate style of the Rover tradition into a completely new age of motoring. The Rover 213. Innovation in style for a range of cars with a big name to live up to. A competitive car in a competitive world. A car that bears the Rover name with pride. The Rover 213 is a car whose name is steeped in the British motoring tradition, a name that means quality, reliability, respect, and above all, style. A style that associates the Rover name with the very roots of quality motor engineering. Exhaustively tested by Austin Rover engineers in some of Europe's most extensive facilities before being given the name Rover. The Rover 213, every inch a driver's car. With features that will impress any discerning motorist with an eye for quality, the Rover 213 suits a variety of motoring needs. For the younger driver, the family driver and the business driver. With features once considered a luxury, the new Rover has an impressive specification of the kind now expected by today's motorist. Each of them incorporated with the aim of making driving more enjoyable and fatigue-free. All of them forming a concept in motoring that puts the comfort of the driver uppermost. Like the fascia and control panel. Designed as a wrap-round concept, putting controls where they're needed and allowing the driver easy access when it counts. Not forgetting the rear seat passengers either, with rear compartment heating as standard across the whole range. Sophistication increases as we go up the range. The S model features add a further touch of refinement. And luxury items on the SE model include tinted glass, central door locking, wood door inserts and exterior brightwork, giving the car an impressive aura of luxury and prestige. And for the ultimate in refinement, the car that combines all the features in one, the Rover 213 Vanden Plas. The traditional symbol of superior quality and pedigree within the Austin Rover range. Leather seat trims of the highest quality giving maximum comfort. Shag pile carpet throughout. An electronic radio cassette player with front and rear speakers for all-round music pleasure. And a headlamp power wash. Seat map pockets. And of course, electrically operated windows and central door locking, with air conditioning as an option. Refinements in comfort and refinements in engineering are complemented with refinements in style. The Rover 213 has a style that sets it apart from its competitors. The smooth, integrated and refined styling theme conveys in an instant all that we've come to expect from a car that bears the name Rover. Inside and out, with the emphasis on luxury, tradition and superior quality materials, the Rover 213 is designed with one essential aim: to achieve total driver and passenger satisfaction. Quite simply, a driver's car. From Austin Rover, the Rover 213. Born to be driven, bred to be Rover. A key refinement offered in the Rover 213 is the new 1342cc 12-valve 4-cylinder aluminium alloy engine. Its design offers significant advances over the competition in terms of performance, economy and sheer drivability. Intake manifold branches of the same length and gas flow characteristics raise the mixture intake inertia effect, and coupled with the 12-valve cylinder head improves low-speed torque and intake efficiency at high engine speeds. And with the distributor mounted on the end of the cylinder head, forward-facing spark plugs and an easily replaced oil filter ensures excellent overall accessibility. Let's take a close look at the power unit, assuming the oil and water have been drained out and the usual auxiliaries have been removed. We can now look much more closely at the Rover's many advanced features. After removing the air cleaner, you'll see that a single twin-barrel carburettor is fitted. The distributor has the igniter unit mounted on its side and is easily removed if necessary. Once the cap's removed, we can check the air gaps are equal and that the electrodes are clean. The distributor cap is sealed against moisture penetration by a rubber seal. And incidentally, it's useful to know that the number 1 cylinder HT lead position is identified by a C mark here, and that the engine turns in an anti-clockwise direction. Now, to remove the distributor, simply undo these 2 nuts and withdraw the unit. Noting the position of the O ring seal as you do, and that the offset drive dog is free to move axially to minimize drive stresses. As you can see, the adapter housing used to mount the distributor also carries the mechanical fuel pump. A few points about the cooling system. This small housing, which is the coolant outlet to the radiator, has a bleed nipple and is used to bleed air from the system as it's being filled. And this housing contains the thermostat and a bypass system which ensures the engine warms up quickly and gives good drivability from a cold start. When the engine starts up, coolant is drawn from this outlet, through the inlet manifold, around the hot spot to this inlet on the thermostat housing. As the bypass valve opens, coolant goes across the housing and back into the water pump inlet pipe, giving a restrictive flow. This restricted circuit allows the coolant to warm up quickly, opening the thermostat and closing the bypass port. Now we can take off the rocker cover to reveal the single camshaft and 2 rocker shafts, one operating the inlet valves with 2 rockers per cylinder, the other shaft having 1 rocker for the exhaust valve. The next step is to remove the timing belt. Remove both timing covers using an extended 10mm socket for this recessed bolt here. Loosen the tensioner bolt and push the tensioner out, like this, and retighten the bolt. What we've done is to create slack in the belt to ease removal and fitting. But remember, if you do intend refitting a timing belt, you must always mark the outside of the belt, like this, to ensure it's refitted in the same direction of rotation. Now we can ease the belt off using fingers only, with the minimum of belt distortion, as the strengthening fibres could be damaged if it's not handled carefully. Remove the belt guides and drive gear, noting the dished face on each guide faces away from the timing belt. Undo the camshaft gear center bolt. Once the gear is removed, these special tools can be used to extract and replace the oil seal without disturbing the housing. Undo and remove the cylinder head retaining bolts and insert a suitable lever at this point here to apply a firm, sustained pressure in order to peel the gasket apart. But be careful, a sudden excessive force may damage the aluminium castings. Undo the rocker shaft bolts, keeping them in position in order to hold the components together as you lift the shafts clear. It's easy to recognize one rocker shaft from the other, since the inlet shaft has twice as many oil holes. Now remove all the bearing housings, noting that they're numbered, together with an arrow as a reference for correct refitting. The arrow points towards the timing belt. The camshaft end float is controlled by a flange on the camshaft running in this groove on the number 5 bearing housing. The camshaft can now be lifted out. After removing the valves in the conventional way, we can see there are valve stem oil seals fitted to both valves, but make sure you know which is which. Those fitted to the inlet valves have a light-coloured spring, whereas the seals on the exhaust valves have a dark-coloured spring. It's also important that the valve spring close-wound coils are fitted next to the cylinder head. And so we move on to the engine block. The crankshaft rear seal replacement. Secure this tool firmly in place. Puncture the seal in several places with the tapered punch. Screw in the self-tapping screws. Now turn the center screw to extract the seal. The same tool is also used to replace the seal. In order to remove the oil pump, we first have to remove the sump and its gasket. The pump, mounted on the front of the crankshaft, can then be dismantled in a similar way to those used on other Austin Rover engines. And so to the heart of the engine. The first thing we notice is the one-piece main bearing cap and the oil gallery along its full length, from which oil is fed directly to each main bearing. Remove this main bearing cap and lay to one side, taking care to retain the shell bearings in their respective positions. The conrods have a bearing identification stamped on the big end, so you'll need to mark the conrod for cylinder location. Now the crankshaft. On closer inspection, you'll notice these letters and numbers stamped on the webs. They're used to enable bearings to be selected to give the optimum running clearance. First, the main bearings. This number relates to the adjacent main journal and is used together with this letter, stamped on the rear face of the cylinder block. And with the chart in the repair manual, read off the colour-coded shell bearing required. Big end bearings are selected using the same method, but this time we use this letter next to the big end journal and this number stamped across the big end cap joint face. The colour is on the edge of the bearing. Rebuilding the engine is the reverse to its strip, but with the addition of a couple of points. When refitting the cylinder head, this sequence must be followed. First, tighten all the bolts equally to half the torque. Then follow the same sequence to the final torque. Next, we can look at the timing belt refitting and its adjustment. First, align these timing marks on the crankshaft. And the camshaft gear marks horizontal with the up at the top. Now slide the belt over the gears and around the tensioner. Loosen this single bolt and allow the spring to pull the tensioner into the belt. Now rotate the crankshaft anti-clockwise to the equivalent of 3 camshaft teeth, allowing the tensioner to correct the tension on the belt. The bolt can now be tightened. To adjust the valve clearance, rotate the crankshaft anti-clockwise until this up mark is at the top and that these 2 marks each side of the drive wheel are aligned with the cylinder head. We can now adjust all the valves on number 1 cylinder. Rotate the crankshaft anti-clockwise 180 degrees to place this mark at the 12 o'clock position. Now we can adjust all the valves on number 3 cylinder. Align these 2 marks again, there's no up mark this time, for number 4 cylinder. And this mark at 12 o'clock for number 2 cylinder. With the engine completely rebuilt, it's now ready to be dropped back into the frame. Again, this is in reverse of the removal. To set the ignition timing is simplicity itself. Set the idle speed to 750 revs per minute and using a strobe light, align this red mark on the front pulley with this pointer on the lower cover. But remember, the engine runs anti-clockwise. Maintaining the Austin Rover reputation of fuel-efficient vehicles, the Rover 213 uses an air temperature control system to maintain optimum carburetor air intake temperature regardless of engine and outside operating conditions. A diaphragm-operated air temperature control valve opens and closes a hot air duct from the exhaust manifold. This air valve, operated by a bimetallic strip, controls the diaphragm operation by venting the vacuum to atmosphere. During engine warm-up periods, manifold depression opens the check valve, raises the diaphragm and control valve, opening the hot air duct from the exhaust manifold and closing the cold air duct. When the temperature in the air cleaner reaches 25 to 31 degrees centigrade, the bimetallic strip opens the air bleed valve, venting the vacuum to atmosphere, allowing spring pressure to push the control valve down closing the hot air duct and opening the fresh air duct. Once the engine's warmed up, the flap remains in a fairly constant position, with sudden flap movement damped by the diaphragm operation. Now to the fuel system. The camshaft-driven pump provides fuel pressure and a spill return back to the tank. When the float chamber needle valve is seated, excess fuel in the system is returned to the tank. A two-way valve located above the tank controls the breathing system, preventing the tank from deforming when the fuel level drops, and it releases excess pressure if the fuel temperature rises. All fuel leaving the tank passes through this filter, located at the front of the tank. The filter should be changed every 2 years or 30,000 miles and must be fitted with the arrow facing in the direction of the fuel flow. The carburettor is a downdraft twin-barrel two-stage type fitted with a manual choke. During normal driving conditions, the primary system is used, giving maximum fuel economy. At idle, fuel is drawn through the primary main jet from the float chamber via the slow-running jet into the emulsion tube, where it's mixed with air from the slow air jet. And adjustments to the mixture are achieved by this adjusting screw, which controls the amount of fuel emitted from the idle port. This emulsified mixture is then drawn into the venturi via the idle port. As the throttle is partially opened, the bypass ports are uncovered, so increasing the amount of fuel delivered. Further movement of the throttle valve increases the depression in the venturi, which draws fuel from the primary main jet into the emulsion tube, where it's emulsified with air from the primary main air jet and emitted through the main nozzle. When additional power is required, the secondary system supplements the fuel already supplied by the primary system. The secondary throttle valve is controlled by this diaphragm, operated by depression in the primary and secondary barrels. Initial movement of the throttle valve draws fuel from the secondary main jet into the slow jet. This fuel is then mixed with air and emitted from the slow port. Further movement of the throttle valve increases the depression, and fuel is drawn through the secondary main jet into the emulsion tube, where it's mixed with air from the secondary main air jet and drawn into the venturi through the main nozzle. Increased fuel for acceleration is supplied by this accelerator pump. When the throttle is depressed quickly, a diaphragm is moved, creating a pressure in the pump chamber. The accelerator pump we've just looked at only supplies additional fuel during immediate throttle openings. Increased fuel required for sustained acceleration and hill climbing is maintained by this power valve in the bottom of the float chamber. This vacuum piston is held up by manifold depression. The power valve is seated and the engine runs on fuel supplied by the primary main jet. When the throttle is opened, manifold depression drops and spring pressure pushes the vacuum piston down, opening the power valve and increasing the amount of fuel flowing into the primary system. A vacuum-operated diaphragm is used as a throttle damper. When the throttle is released, the depression is reduced gradually by this check valve in the vacuum line. This has the effect of closing the throttle valve gradually, providing a throttle damping effect. To prevent running on, the slow system is equipped with a solenoid-operated fuel cut-off valve, which cuts the fuel off when the engine is stopped. Now carburettor tuning. Before tuning the carburettor, the ignition timing spark plug gaps and valve clearances must be correct. And then, making sure there's no electrical load on the alternator, adjust the idle speed. After connecting a CO meter and removing the tamper-proof cap, adjust the mixture screw to obtain a reading of no more than 3%. Recheck the idle speed and CO reading and adjust as necessary. And that completes the basic checks to the Rover 213 fuel system, ensuring a consistent supply of fuel to the power unit at all times and contributing to smooth Rover-style motoring. In addition to the many refinements on the Rover 213, a 5-speed manual gearbox is fitted across the range, giving obvious advantages of increased fuel economy, as well as adding that extra refinement to high-speed motoring, especially on that longer journey. The cable-operated diaphragm spring clutch is adjusted at the gearbox end of the cable to give a clearance of 4 to 5 millimeters at the tip of the release arm. For maintenance purposes, the removal of the gearbox is straightforward and can be carried out independently of the engine. And to absorb transmission wind-up, the drive plate has 4 rubber torsion dampers, giving a smooth, progressive clutch action. The 5-speed gearbox is constructed from 3 castings: the clutch housing, the transmission housing and the 5th gear housing. First, remove the bolts to the 5th gear housing, the reverse light switch and the housing. The main shaft end float is controlled by a spring ring and selective snap ring inside the back of the 5th gear housing. Setting is easy, as we'll see during reassembly. Next, dismantle the 5th gear assembly, starting with the main shaft bearing, which simply lifts off. Drift out the roll pin from the 5th gear selector fork. Raise and lift off the selector fork and 5th gear synchro assembly. Now position the main shaft holder onto the main shaft. Now, by turning the selector shaft clockwise, select reverse gear to lock the main and counter shaft and undo the counter shaft nut, making sure the staking has been knocked fully back to avoid damage to the counter shaft. With the nut removed, turn the selector back to the neutral position. Remove the 5th gear from the main shaft and also ease off the corresponding countershaft 5th gear. The main shaft 5th gear will only fit one way and runs on a caged needle roller bearing with the non-selective thrust washer providing a predetermined end float. Next, remove the 3 selector shaft capping bolts, balls and springs which control the detent position of the selector shaft. Now we can undo the 11 bolts connecting the transmission housing to the clutch housing and remove the 2 dowels from the transmission housing to allow the puller to sit flush with the housing face and pull the housing off. It's important to remove the 2 dowels, otherwise damage could be caused to the threads in the casing where the puller is located. As the housing is being drawn off, gently tap the clutch housing with a soft-faced hammer to free the dowel and ensure the transmission housing is pulled off square. Next, remove the reverse idler shaft and gear. Remove the nut and keyed washer from the reversed shift fork. And remove the fork, taking note of the detent ball size in the clutch housing. Next, knock back the retaining tabs, undo the selector fork bolts and remove the forks and shaft in sequence. To remove the 1st and 2nd speed fork, engage 2nd gear, ease the fork around and remove. Now remove the main shaft and counter shaft as an assembly. These simply lift out. Undo the 4 bolts locating the shift arm holder, noting that the 2 outer, darker ones are dowel bolts which shouldn't be mixed on reassembly with the 2 inner retaining bolts. An interesting point worth noting is that incorporated in the shift arm holder is a reverse gear lockout device which prevents engagement of reverse gear when coming out of 5th. Now lift out the final drive and you'll notice the speedometer is driven directly off the final drive. Right, that's covered the major dismantle procedures. Now we'll go through some of the points worth noting during reassembly, which is done more or less in reverse order. The differential end float is controlled by this selective circlip, located in the transmission housing, and is adjusted when the gearbox is reassembled. An important point, if any of the synchro hubs have been dismantled intentionally or otherwise, is that on close examination you'll notice that all synchro sleeves have 3 sets of longer teeth, which when reassembled must be matched with the corresponding deeper grooves in the hub. Once the countershaft has been built up, 1st, 2nd, 3rd and 4th gear end floats can be checked using a feeler gauge between the gears and their respective thrust washers or spacers. The reverse fork has a slightly larger detent ball and shouldn't be mixed up. Although the larger ball will fit in the selector detent ball drillings, it won't move freely inside the capping bolt and can jam up when the capping bolt is tightened. This could prevent positive detent location when the relevant gear is selected, causing poor gear selection and could lead to auto disengagement of the affected gear. The main shaft end float, which we talked about earlier, is set as follows. After removing the selective snap ring and spring ring from the 5th gear housing, place a straight edge across the face, and with a depth gauge, measure the depth between the spring ring seating and the straight edge. Subtract the thickness of the straight edge and make a note of the reading. Now measure the distance from the top of the bearing outer face to the uppermost face of the transmission housing. Make a note of the reading and subtract this measurement from the first one taken, and from this figure subtract the spring ring free height of 0.85 millimeters. This final sum is the thickness required for the selective snap ring. The gearbox reassembly can now be completed. To give faultless handling under the most arduous road conditions, yet provide the kind of driver comfort for which the Rover name is famous, the Rover 213 features front torsion bar and strut with rear beam and trailing arm suspension. Road shocks at the front of the vehicle are absorbed by the torsion bars, with the struts dampening body movement and a stabilizer spring connecting the radius arms through rubber bushes, adding stability when cornering. The steering system is maintenance-free, with mechanical adjustment limited to the rack damper and front wheel alignment, with steering column adjustment to give the optimum driving position using this lever. Forward and rearward movement of the front suspension is controlled by forged spring lower arms. And a further refinement is the use of negative offset geometry. This is achieved by designing the mounting of the front dampers and lower ball joints in such a way that their axes meet at the road surface outside the tyre centre line. Under braking conditions, the front wheels pull inwards, giving an equal and opposite force to body sway, thereby keeping the car straight. The mounting position of the front struts has also made the low bonnet line possible, and with major components mounted to the rear of the front wheels, the possibility of front suspension damage on minor vehicle impact is reduced. The suspension design also gives major front-end anti-dive characteristics by locating the radius arm pivot points behind the centre line of the front wheels. The braking torque is transmitted upwards, opposing the nosedive tendency, and together with the anti-lift design of the rear suspension, vehicle instability and passenger discomfort under heavy braking is minimised. Well, now let's look at the suspension in more detail, starting with the torsion bar removal. Lift and support the front end. Undo and remove this height adjusting nut, which takes the tension off the torsion bar. Undo and prise off the torque tube holder and rubber capping, and remove the circlip. After removing the rubber dust cap from the lower arm, tap the torsion bar approximately 10 mm forwards. And remove the retaining ring from the front. Drive the torsion bar rearwards and remove it from the vehicle. Along with the rubber-mounted torque tube and integral height adjuster. You'll notice that the torsion bar and torque tube are located by a master spline. The torsion bars are pre-stressed and stamped, indicating their direction of operation, and they must not be changed from side to side. Once the torsion bar has been reassembled and the car lowered, bounced up and down a few times to make sure it settles, and push forwards to remove tyre scrub, the trim height can easily be measured and reset. Measure the distance between the wheel arch and the ground. Yes, that's right, the ground, not the hub centre, so it's vital that the ground is level and the tyres are at the correct pressure. Lift the wheel clear of the ground and adjust the trim height. Tightening the nut clockwise raises the vehicle height, and loosening lowers it. One turn of the nut alters the height by approximately 5 mm. Changing a front damper is simplicity itself. After lifting up the front of the car and removing the wheel, undo the brake hose clamp. And using a jack to support the lower control arm, undo the lower pinch bolt. Carefully lower the jack whilst lifting the strut out of the knuckle, then undo the self-locking nuts in the engine compartment, compress the damper and simply lift it out. Road shocks to the rear of the vehicle are transmitted from the wheels through the axle beam and absorbed by the coil springs and dampers. The main purpose of the trailing arms is to provide a location for the rear suspension and stabilise forwards or rearwards suspension movement. The right-hand trailing arm is fitted to a swing bearing, which in turn is attached to the brake backplate, whilst the left-hand trailing arm is bolted directly onto the backplate. A panhard rod is mounted at one end with rubber bushes on the right-hand side of the axle tube, and at the other end with rubber bushes in a bracket attached to the body. Its primary function is to limit lateral or sideways movement of the rear suspension, keeping the axle in a neutral position when cornering. Although, as we said earlier, the main purpose of the trailing arms is to provide forward and rearwards location of the suspension, the design with the trailing arms connected to the rear backplates gives excellent anti-lift characteristics at the back of the car when braking. To get a better look at the rear suspension system, we'll remove the whole unit, which is a very straightforward procedure. Support the axle tube, and holding the damper shaft with an Allen key, disconnect the rear damper self-locking nuts in the boot. Finally, disconnect both trailing arms and the panhard rod from the body. And lower the complete rear suspension. Now onto the brakes. The dual circuit, diagonally split, front disc, rear drum braking system holds no real surprises. A dual-purpose proportioning valve limits brake fluid pressure to the rear wheels under heavy braking and also directs pressure to the remaining brake circuit if the other fails. The front brakes use the single-piston floating calipers design with large area brake pads to give long life and provide fade-free stopping power. And access to the pads is in the now familiar way. To replace the brake disc, completely remove the caliper, making sure it's supported to avoid strain on the brake hose. Undo both countersunk screws and simply lift off the disc. Rear brakes are self-adjusting leading and trailing shoes. And the handbrake adjuster is accessible from inside the car at the rear of the handbrake console. The brake servo is serviceable and push rod adjustment is made with this adjustment gauge, and full details are given in the repair manual. When overhauling, always use all of the components supplied in the repair kit, making sure all seals are lubricated. Rover 213, the driver's car. The car designed for performance, economy, space, but above all, the car with style, functional style. And a car designed for service and repairability. The attractive polypropylene colour-keyed bumpers have a positive function. They're designed to withstand those minor parking knocks without damage and are easily removed. After undoing the access panels, 6 bolts retain the bumper. The design relies on flexibility to absorb low-speed impact without damage. So the paint finish must be able to flex without cracking or peeling, yet be tough enough to resist stone chips. Replacement bumpers are supplied unprimed. A special adhesion promoting primer must be used, followed by a 2-pack colour code system with the addition of a plasticizing agent. The Rover name has been a byword for driver and passenger safety, with previous models winning the coveted Don Safety Award. The Rover 213 is in the same class. The complete bumper mounting brackets have built-in collapsible sections and can easily be replaced. Further collapsible sections, front and rear, not only provide maximum driver and passenger protection, but also offer minimum accident repair costs in both private and fleet user. The headlights are adjusted with these 2 screws, the outer one for vertical adjustment and the inner one for horizontal adjustment. And with the bumper removed, the headlamp can easily be replaced by undoing 4 mounting bolts. A further example of the Rover's repairability is the front mask panel, which is simple to remove, and so are the front wings. With plastic liners to further improve corrosion protection. The now familiar flush glazing not only contributes to the car's good looks, but also reduces drag and wind noise, whilst adding to the body strength. This allows the use of narrow body pillars, bringing about a reduction in body weight and giving the driver excellent visibility. Screen removal is achieved using the fast cut equipment. Wrap-over doors not only eliminate drip rails and gutters, reducing drag, but also give easier driver and passenger access, with the door frame providing a channel to direct water swept by the wipers away from the side windows. And better visibility means safer driving. The rear doors also house operated window winders, with the simplicity and compactness of design giving a significant weight reduction and enabling a reduced door section thickness to be used, allowing more interior space. To facilitate accident damage repair, hinges are bolted to both the door and the A-post. A one-piece body side pressing is used during manufacture, which keeps all door aperture dimensions constant, guaranteeing an optimum door fit. The Rover 213's wedge shape not only gives excellent aerodynamic qualities, but also provides a huge amount of fully usable boot space, with the rear suspension dampers mounted to give minimum boot intrusion. Add to this the ski hatch available on most models, and the 213 becomes a class beater, significantly better than most competitors in its class. Rear bulbs are easily replaced after removing the inspection cover, with the stop and tail lights featuring double filament bulbs in case one blows. With the one-piece boot mat lifted back, the spare wheel and jack are easily reached. A central jacking facility is also provided, front and rear, for garage use. Inside the car, a full range of fuses are easily accessible. Fuse replacement is simplified with this tool located in the fuse cover. And after removing just 4 screws, the instrument binnacle can be moved forward, allowing access to the instrument pack. The Rover 213, the driver's car which offers all that's best in safe, sensible design, as well as eye-catching good looks. The Rover 213. Refinements in motor engineering that provide for tomorrow's style of motoring right now. With a distinguished record in providing driver satisfaction, Austin Rover enhances the Rover name with all that's best in modern motoring technology. The Rover 213 is the result of years of research, development and intensive testing. The aim, to develop a car with instant Rover appeal and satisfaction. Rover 213, the latest example of engineering excellence from Austin Rover. The car with an impeccable pedigree. Rover 213, born to be driven, bred to be Rover.